Design and simulation of off-grid solar/mini-hydro renewable energy system using Homer Pro software, case of Muyuka rural community. Abstract electrification in remote areas is constrained by technical barriers like long-distance transmission network, rugged terrains, and highly dispersed population. The low population density characterized by a low level of education implies low load density and low revenues. These characteristics hinder investors from investing in the rural sector. In many parts of Cameroon, electricity generation is often non-existent or unreliable and erratic. Cameroonian rural population outnumbers urban inhabitants, and it is precisely in these rural regions that the lack of reliable infrastructures and services is all the more problematic. These shortfalls are persistent and structural, and the amount of capital required to fix them is tremendous. The usual approach to centralized generation and distribution may not be able to solve this problem. Presently, households and businesses that can afford resort to using diesel generators which are not environmentally friendly and very expensive to run. Replacing multitudes of diesel generators with hybrid solar/mini-hydropower plants can substantially reduce cost and climate impact. In this context, the development of off-grid decentralized solar/mini-hydropower systems, or of systems built around a mini-grid, proves to be appropriate. This solution would help to stem the tide of people abandoning rural areas, which is a problem severely affecting the country. This paper is dedicated to the design and implementation of a hybrid solar/mini-hydro renewable energy system for the rural community of Muyuka subdivision. The consideration evolved from being focused on the concept of hybridization of photovoltaic, PV, and hydroelectric power plants. Homer Pro is used for the simulation. Homer Pro integrates components, resources, and economic calculations. It simplifies the task of evaluating the design of off-grid for a variety of applications. The result will be a suggestion on how the Muyuka rural community could sustainably be electrified by using renewable energy-based off-grid power system. This contribution will be a vital tool to the policymakers and implementers of renewable energy systems in Cameroon, considering the case of the Muyuka rural community. Keywords: off-grid, decentralized solar/mini-hydropower systems, mini-grid, hybrid renewable energy system, Homer Pro, simulation. Introduction. Background of the study. Electricity is an imperative condition for a country's development. Without electricity, people's livelihood options are limited, access to essential services is restricted, and quality of life is adversely affected. The traditional approach to serving rural communities with electric power is to extend a central grid. This approach is technically and financially inefficient due to a combination of capital scarcity, poor energy service, reduced grid reliability, extended building periods and construction challenges to connect to remote areas. The governments and other funders have recognized that reaching rural communities through the expansion of the national grid can be costly and slow, and is sometimes not feasible. Adequately financed and operated mini-grids based on renewable energy can overcome many of these challenges. Statement of the problem. The Republic of Cameroon has an ambitious target of providing electricity to everyone in the so-called Vision 2035. This is intended to transform the country into a middle-income economy. Regarding renewable energies, Cameroon in its National Development Contribution, NDC, to reduce greenhouse gas as part of 21 Colombian pesos, leading to the Paris Agreement, decided to have 25% renewable energy in the electricity mix by 2035, from less than 1% today too. The development of renewable energies is one of the strategic plans for the reduction of poverty so that the country could end up with a developed economy. One way to contribute to the realization of this objective is in the design and implementation of a hybrid solar/mini-hydro renewable energy system for rural electrification. Mini-grids can be energized by using renewable energy based on hybrid system technology into which multiple combinations of renewable energy technologies can be integrated. Standalone systems are costly to acquire and maintain. 3. Mixing different technologies with different energy sources provides competitive advantages compared to using a single technology. For example, the solar PV system peaks up when hydro generation drops during the dry season and vice versa. The battery backup system adds stability to the network by storing the energy for peak consumption when there is insufficient production from renewable sources. This template, modified in MS Word 2007 and saved as a Word 97 to 2003 document for the PC, provides authors with most of the formatting specifications needed for preparing electronic versions of their papers. All standard paper components have been specified for 3 reasons: 1. Ease of use when formatting individual papers, 2. Automatic compliance to electronic requirements that facilitate the concurrent or later production of electronic products, and 3. Conformity of style throughout a conference proceeding. Margins, column widths, line spacing, and type styles are built in. Examples of the type styles are provided throughout this document and are identified in italic type, within parentheses, following the example. Some components, such as multi-leveled equations, graphics, and tables are not prescribed, although the various table text styles are provided. The formatter will need to create these components, incorporating the applicable criteria that follow. See objectives. The main objective of this research is to develop a framework for the optimal design of a renewable energy system which incorporates many hydro and solar components for the Muyuka rural community. This global objective entails the following specific objectives: 1. To develop a hybrid solar/mini hydropower model for the Muyuka rural community, and 2. To evaluate the performance of the solar/mini hydropower system performance based on system generation and load demand. D. Literature review. The initial cost of microgrids is often a barrier to its development. The financial cost of distributed energy resources is perceived to be higher than that of a centralized power generation system. Recent studies, however, have found that the cost of generating power in a microgrid is comparable with present electricity supply as long as support for PV is available for. Again, instead of investing in new infrastructure to meet increasing demand, microgrids can be used to solve the peak load problems, especially in low load density rural communities. In developing countries without infrastructure like Cameroon, microgrids are more likely to be cost-effective since the installation cost must be compared with that of installing high-voltage transmission lines. In the grid-connected mode, the system voltage and frequency are fixed by the primary grid. In island mode, keeping demand and supply balanced to maintain voltage and frequency is a huge task. Various researchers have used different methods for design, implementation, and optimization of the hybrid renewable-based power system. Kenfak et al. 5 in the study Feasibility Analysis of Solar Photovoltaic and Micro-Hydro Hybrid Power System with Battery Storage, at Batoka, Cameroon, the authors compared different combinations of component sizes and quantities. They explored how variations in resource availability and system costs affect the cost of installing and operating different system designs using Homer Pro software. Bilal Abdullah Nasir 6 in the Research MATLAB simulation procedure for the design of micro-hydroelectric power plant concluded that, as micropower continues to grow around the world, it is essential to show the public how feasible micro-hydro systems are in a suitable site. Ashish et al. 7 in their study on hybrid power generation system concluded that to avoid interruption of power by a standalone renewable energy source, hybridization of renewable energy sources is the key. The hybrid energy system has good reliability, efficiency, less emission, and lower cost. The papers reviewed shows the degree of concern that scholars have towards the subject. A hybrid system that includes solar PV/small hydro/storage systems is most appropriate for Cameroon, given that these resources are abundant in the country. 2 Materials and methods. A study location. Muyuka is a town in Foko division in the southwest province of Cameroon as shown in Figure 1a. Muyuka is the headquarter of the Muyuka subdivision. The specific location is at 4°17.4 N and 9°24.9 A. The subdivision is made up of mostly rural communities with sub-villages such as O, Ekta, Bafia, Mwenga, Yoke, Maland, Minja and Bundu. Muyuka has a population of 86,268, with a rural percentage of 67.5%. Muyuka had a hydropower plant constructed in 1947 at the Yoke River known as the Yoke Hydropower Plant. The Yoke Hydropower Plant, Yoke had a hydropower plant with a hydro capacity of 3.27 MW constructed during the period 1947 to 1949. It was part of the Electricity Corporation of Nigeria, given that at the time, southern Cameroons was being administered from Nigeria. The installed power was 2.2 MW but the peak demand at that time was only 1.59 MW9. When the southern Cameroons left Nigeria, the plant was taken over by Powercam Corporation. The installation was dismantled after reunification with La République du Cameroun. Presently, with the advent of modern technology, the hydropower plant can be reharnessed to serve as a mini hydropower plant to alleviate the regular acute power shortage bugging the country. The scraps of Powercam remain standing in Yoke village. B. Resource potential. Cameroon is blessed with enormous and varied resources for electricity production. The hydraulic potential is estimated at 20,000 MW according to the Energy Situation of Cameroon, SEC, 2015, of which only about 5% is exploited, the second largest in Africa after the Democratic Republic of Congo 10. The hydraulic potential is sovereign, as all the rivers that can be used are within the frontiers of Cameroon and not shared with any neighboring country. In the electricity mix of Cameroon, solar/mini hydro energy contributes less than 1% of the 1,600 MW generated 10. Again, The average solar radiation in Cameroon ranges from 4.5 kWh/m2/day in the southern part of the country to 5.7 kWh/m2/day in the northern part of Cameroon, with the highest values in the far north region 11. Therefore, the potential to harness solar/mini-hydropower systems are hugely available in the country. According to 9, the hydropower capacity of the Yoke power plant is 3.27 MW. The considerations for this case study are to design a hybrid solar/mini-hydropower system that can supply 3 MW of power to an AC load. The hydropower system is expected to supply a peak power of 2 MW in the rainy season and 1.2 MW in the dry season, leaving enough residual flow for the survival of biota. For a standalone hybrid system in which the load depends on intermittent energy sources such as solar and run-of-river hydropower systems, reliable backup systems are necessary. In this project, a battery bank is included to provide backup. The backup system also helps to optimize the sizing of the hybrid system. See data collection and load profile. Load demand: the rural population of Muyuka subdivision is about 60,008. With an average energy demand of less than 5 kWh per month, the maximum demand of the community is about 3 MW. The site daily load profile, seasonal load profile and yearly profile are shown in Figure 2. The community load profile for the project has a peak load of 3 MW, including a random variability of 10% daily and 20% time step. Community load profile. Solar and hydro resources: the solar resources are obtained from the National Renewable Energy Laboratory database as shown in Figure 2. The site temperature profile is obtained from NASA's Surface Meteorology and Solar Energy database. As shown in Figure 3, the average solar radiation is 4.49 kW/m2/d, and the average clearness index is 0.51. Figure 4 shows the site temperature profile. The existing data from 9 is used for the hydropower system design. The hydro-scaled annual average flow rate is 22.17 m3/s, and the minimum residual flow is 1 m3/s. Fig 5 shows the hydro resource input. Solar resource inputs. Site temperature profile. Hydro resource input. D. Equipment selection and project optimization. Photovoltaic array: the PV modules used is generic. The PV array size is estimated from the load demand. The considered PV system rating is 1,800 kilowatts, but the sizes considered for the simulation are 1,500 kilowatts and 1,800 kilowatts. The initial cost, replacement cost, operation, and maintenance cost are adjusted to cover the balance of system cost and others. The solar module parameters are shown in Table 1. Batteries. Batteries are an integral part of hybrid renewable energy systems. The battery backup adds stability to the network by storing energy during peak generation and releasing the energy for peak consumption when there is insufficient generation from renewable sources. The battery considered for the project is a lithium-ion 1 mWh capacity battery with supplier integration into Homer Pro. The specifications and price are provided in the software. The battery model parameters are shown in Table 2. Converter. The bidirectional converter is used to interface between the DC bus connected to the PV system and the AC bus powered from the hydro system. A generic large free converter was selected from the Homer database to allow battery sizing without having to size the converter for different S and charging configurations such as load following, LF, and cycle charging, CC. The inverter and rectifier efficiencies of the converter were taken as 95% each. Table 3 shows the converter model parameters. Hydro turbine. The hydro system is made up of the hydraulic equipment, which includes the intake gates and trash screens, the electromechanical equipment which consists of the turbine, generator, transformer, and controls. Table 4 shows the parameters of the hydro turbine. Operating strategies. There are two types of dispatch strategies in Homer Pro: the load following, LF, dispatch, and cycle charging, CC, dispatch. In the load following dispatch strategy, renewable power sources charge the battery, but the generators produce just enough power to meet the load demand. In the cycle charging dispatch strategy, whenever the generators operate, they produce more power than required to serve the load, with the surplus electricity going to charge the battery bank. With the setpoint state of charge chosen, the generators charge the batteries to a set point of about 80%, and the load following dispatch strategy is used to top up the batteries. Table 5 shows the system control inputs for the simulation. F cost. Figures 6 and 7 from 12 shows the total installation cost range for PV and hydropower renewable energy installations. The figures are used as a guide in choosing the cost range for the PV and hydropower renewable energy installations. Simulation and optimization with Homer Pro. Fig 8 shows the system architecture. Microgrids are by their nature very dynamic systems in which several variables can be changing simultaneously and continuously. The solar resource has a very erratic behavior following local meteorology, and loads can change rapidly and subject the system to peaks and transients. Batteries and electronic devices have their logic and response to changes in electric parameters. The interaction of all these variables and behaviors can result in a very complex system to analyze. Microgrid modeling and simulation is done to optimize the technical performance and economic viability. The simulation serves two purposes. It determines firstly whether the system is feasible, that is being able to serve the electric load, and secondly, it estimates the life cycle cost of the system. The life cycle cost is represented by the total net present cost, which includes all costs and revenues that occur within the project lifetime with future cash flows discounted to the present. Homer Pro's 1-hour time step is sufficiently small to capture the most important statistical aspects of the load and the intermittent renewable sources and equally appropriate to allow computation to the extent that optimization and sensitivity analysis can be handled. The hydropower is operated at rated capacity at all times to provide frequency and voltage stability and improve on system components and configuration. System efficiency. The solar PV system is used to balance the supply. At peak load periods, the storage system comes in to support generation. During periods of low demand, excess generation from the hydropower is used to charge the storage systems. The stored energy can then be used to provide energy during periods of high demand. Results. The proposed system involves hydro, solar PV, batteries, and a converter. The energy sources are hydro and solar power sources. The supportive component used to improve stability and reliability is the battery bank. An inverter is included for power conditioning. The mini-hydropower interconnects with the PV solar system. The DC bus voltage is 1.2 kV, which is converted to 400 V, 3-phase, 4-wire by the converter for connection to the AC bus. The local community is powered from the AC bus. Figure 9 shows the simulation result. The results show that the solar PV rating of 1,800 kilowatts, 16 units of 1 mW batteries, 2 MW hydro generating 1,834 kilowatts peak and the converter operating at 1,711 kilowatts are the optimal combinations. The dispatch strategy is cycle following, CC. The net present cost, NPC, is $26.3 million and the initial capital required is $17.4 million. The operation and maintenance cost per year is $823,643. For the optimized system, the cost of energy is $0.628. Fig 10 shows the optimal result based on least cost of energy, CO. Best option by Homer Pro. Discussions. The results highlight the fact that the use of Homer Pro as a design and simulation tool in the design of microgrids and optimization of various renewable energy installations is quite extensive. The study covers the design and implementation of a hybrid solar/mini-hydro renewable energy system. The main objective of the research is to design and evaluate the performance of a rural electrification project using hybrid autonomous renewable energy systems. Sources considered were hydro and solar PV systems. The results show that renewable energy can play a satisfying role in providing electricity to rural communities. The results of the design can be improved if actual costs are obtained from the manufacturers and suppliers. The study also illustrates the fact that hybrid renewable energy systems, though small-scaled, are endowed with high operational and constitutive sophistication. However, modern technology allows reliable and cost-competitive energy generation in remote areas, surpassing the convenience of traditional solutions using grid extension or diesel generation by economic and environmental considerations. The results demonstrate that the system offers the least cost of energy for the required quality and level of service. In some instances, the most practical system might not be the most cost-effective. In the simulation results, the optimal system provided by Homer Pro has a net present cost, NPC, of $26.3 million and cost of energy, $0.268. The researchers found the least cost of energy in the simulation is $0.168. An NPC of $26.4 million, which is much lower than that proposed by the software. The system supply equally matched the village demand with very little shortages. Adjustment of the dot of the battery storage system could be used to offset the shortages. Despite the many benefits of the system, the energy cost of $0.162 is higher in comparison to the residential grid tariff in Cameroon, which ranges from $0.083 to $133 for low-energy consumers. Conclusion. A careful prospection of resources has to be made, as well as the characterization and analysis of the loads. This leads to the better design of the generating components and storage system that converts the variable and intermittent availability of resources into a continuous and reliable electric supply. Collecting meteorological data at the site is the .rst step of the hybrid design. The solar energy potential can be estimated by consulting solar radiation maps, satellite images, NASA and NREL databases, or by measuring global radiation at the site. With this data, it is possible to determine the available solar resource by the calculation of the peak sun hours. Sizing of these sources requires performing multiple simulations in scenarios of days or months. The use of Homer Pro as a tool in the simulation and optimization of various renewable energy installations in a small power system project has been quite extensive as seen in the results. The software provides much flexibility in defining load, system architecture, energy sources, and dispatch strategies. However, the software does have limitations. The models for the load, PV array, battery bank, inverter, hydro turbine, and all the renewable energy components must be developed by the designer either through auxiliary programs or by using paper and pencil and manual inputs or obtained through cooperation with research institutions that have developed proprietary models. While Homer Pro makes simulation and optimization relatively easy, designers need appropriate data and logical assumptions in order to come up with sensible results. The cost results can be improved greatly if the designer obtains the cost of components from the manufacturers and suppliers. Realistic results can also be obtained if the resource assessments are based on real field measurements, but this demands time and considerable expenditure. Energy storage is amongst the most expensive component and cost driver of these systems as shown in the cost summary table, not only because of its initial cost that can represent nearly half of the total investment but because of the periodical repetitive renewals along the expected lifetime of the microgrid. The advent of lithium batteries brings the possibility of a better performance at a lower long-term operating cost. This paper has highlighted the potentials of Homer Pro and its application in the design of many power systems. Homer Pro software can significantly simplify and shorten the process of many power system design.